we're thrilled to have Leah Buechley back to the CU campus. As some of you, I think, know, Leah is a graduate of CU's College of Engineering and Applied Science and earned both her Ph.D. and master's degree in computer science here. She's currently an associate professor at MIT and directs the High-Low Tech Research Group, which pairs high technologies such as circuits and electronics with low technologies like wood, paper, and paint. And the results, like electronic textiles, are fun and engaging ways for young people to design and develop tech-related arts and crafts. Leah will share some examples of these high-low tech projects and talk about how this work is an important part of getting more students exploring engineering and developing their own technologies. In addition to being featured in many publications, her research was the recipient of a 2011 NSF Career Award. Leah's work meshes well with the speaker series, through which Atlas brings in technologists and innovative thinkers as a way to start conversations and explore the ways in which technology is shaping society and vice versa. The Atlas Speaker Series is possible because of a generous donation from Edith Harrell-Caperton and Anat Harrell. Leah has been very generous with her time here at CU, and in addition to this talk, she'll be participating in a number of panels as part of the Conference on World Affairs. So we hope that you're also able to hear her at her other speaking engagements this week. Please join me in giving a warm welcome to Leah Buechley.
Thank you so much, Jill, and thank you so much, Stephanie, for all your help. And I'm really delighted to be here today. It's a special treat to be able to come back to campus and to reconnect with old friends and colleagues and share some of the work that I've been doing over the past about, 5 years since I've been away from here. So what I'm going to talk about today is the research that my students and I have been doing in our group, the High-Low Tech group. And I'm going to talk about work that I've done and also work that we've done collaboratively and then work that individual students have done. So I wanted to, before I start, kind of give due credit to all of them. So work that you're going to see has been done by Jennifer Jacobs, Sam Jacoby, Emily Lovell, David Mellis, Ji Chi, Kanjun Q, and Amit Zaran. So the focus of our work really involves integrating art and craft and technology. And as Jill said, that involves a few things. So that involves integrating kind of high-tech stuff and low-tech stuff. That involves integrating design and engineering. And that involves integrating physical and intellectual building practices. We approach that work in kind of two different ways. On the one hand, we are designers ourselves, and we design and we build objects. But the more important aspect of what we do is to design and build experiences for other people. So design tools and materials and activities that enable other people to create artifacts themselves. So I'm going to talk about these two aspects of our work today. And I wanted to start by talking about artifacts and how we approach designing stuff when we work as designers ourselves. Kind of what are some of the themes that guide that work? So the first theme that I wanted to talk about is craftsmanship. And rather than continue talking, I wanted to show you a couple of projects. So this is a project that I had the great good fortune of working on with my parents, who are both master woodworkers. So they designed and built the wood construction here, and I designed and built the the electronics. So this is a simple object. This is a lamp. And the way that it works is you can kind of place your hand anywhere along the ribbon of wood, and the light will gradually flow out from the spot that you placed your hand. And then to turn the lamp off, you do the same thing. So you can place your hand on the surface of the wood, and then the darkness will gradually flow out from the area where you placed your hand. So that's one example. I wanted to share a second one. So this is a project done by Amit Duran. So what he did is he built a series of ceramic vases in very traditional following very traditional kind of ceramic craft processes. So he cast these vases in clay. He then glazed them and fired them and glazed them and produced these really wonderful kind of traditional ceramic forms. Then he took several of those forms and he intentionally broke them. So he threw some of them on the floor and he kind of banged some of them with a hammer. Then he took those broken vases and using his computer and some digital design software, he replaced the broken pieces of vases with a digitally designed form, which he then printed out using a 3D printer. He then kind of reassembled those broken vases into these hybrid forms where part of the vase is made by hand using traditional craft practices, and part of the vase is made through these very contemporary digital practices. So both of these examples get at what I mean when I say craftsmanship. So we're very interested in exploring the whole rich variety of the traditions of human making, and then finding ways to integrate those traditions of making and designing with contemporary traditions and contemporary techniques and approaches. The next theme that I wanted to talk about is what I'll, for lack of a better term, call material bravery. By which I mean that there's this kind of wondrous array of materials out in the world. So there's paper and paint and dirt and grass, rocks and ceramics and textiles, and they're all wondrous, marvelous things. And it's a shame that we don't encounter those when we interact with our technology. So we're interested in finding ways to integrate the richness of the material world with new technologies, and in particular with electronics and computation. So you see one example of that here. So this is an origami construction built by my student Ji Chi. So this is an origami crane, a folded paper construction that has integrated electronics that allow it to flap its wings. So there are mechanical elements in there that allow it to change shape. The final theme that guides our work as designers that I wanted to talk about is beauty. So we're interested in things like shape and color and pattern and form. And we think that beauty is a profoundly important part of many people's experience of the world. It's certainly a really important part of my experience of the world. And that deserves explicit attention and investigation. And so we think that beauty is as important as utility, and that it's as important as kind of the conceptual underpinnings of a work. And so we like to explicitly think about it and incorporate it into our designs. So this is a piece that really is exploring pattern and color and so on. So this is one in a series of interactive wallpapers that we built. The way that this is made is that it's essentially a large interactive circuit board that's painted using electrically conductive paints. That turns a large surface into an interactive input-output device. So on this surface, there are sensors that monitor the environment, like light sensors and temperature sensors and movement sensors. And then there are also touch sensors, which allow you to interact with the device. And then there are display components that are incorporated into the piece. So there are these LED lights that can be lit up in different patterns. And then this piece is also networked, so it can communicate with other devices and display information that way. So let me show you one example kind of program kind of running on a piece of this wallpaper. So there what you saw was a person kind of touching the wall and interacting with it, and that interaction was creating these bird songs that were being played by a computer that was connected via the network. Okay, so I've shown you a couple of the artifacts that we've designed and talked about the themes that guide that work. I now wanted to shift and spend the remainder of the talk on talking about experiences and the experiences that we facilitate for other people. So we're focused on engaging different kinds of people in creating their own artifacts, and in particular, helping people build artifacts that are kind of like the ones that I just showed you. So helping other people make stuff with technology that's beautiful and material and respects craftsmanship. We do that in a few different ways. So we do that by teaching workshops to people where we engage them in making stuff. We do that through designing and publishing tutorials, both online and in print. We do that by designing and disseminating construction kits that help people work with new craft and art materials and combine those materials with technological materials. And then finally, we do that by publishing a lot of the source code for the work that we do online in an open manner. So those are some of the ways that we engage the world with our work. I wanted to just briefly go over the audience that we're really targeting with this engagement. So we really are primarily interested in engaging technological novices, so people who haven't previously had experience building electronics, say, or programming computers. We tend to focus primarily on middle and high school students, although we kind of engage with a wide range of people, but that's our primary focus. And then the intent of our engagement is not necessarily to teach them any particular concept, but rather to get them excited about these materials and tools and disciplines, get them excited and engaged, and to hopefully give them the sense that these are spheres that they can operate in with power and with fluency and with agency. That technology is something that they can understand, that they can control, and that they can ultimately create. So now I'm going to talk about a few different realms within which we do this work and kind of give you some specific examples of projects where we're engaging other people in creating technology themselves. So the first sphere that I wanted to talk about is consumer electronics. So we're all super familiar with devices like this. So our lives are filled with electronic and computational devices of all shapes and sizes. So if you think about your life, you know, your stereo, your microwave, your toaster, and certainly your smartphone and your computer, those are all these powerful electronic computational devices. And so we thought, wouldn't a really powerful and cool way to help people feel like they could understand and control technology be to have them make their own devices like this? So have people make their own consumer electronic devices. So my student, David Mellis, has been working on a project along these lines. So he's developed a series of designs for typical consumer electronic devices. He's developed those designs himself first. So you can see one example here. This is a set of iPhone or computer speakers. And then he's published those designs freely and openly on his website. And then he's taught workshops where he engaged people and had them make replicas of these canonical consumer electronic devices themselves and had them kind of tweak the designs as they were interested to do. One thing that I'll just mention here is to note that there are like 3 axes of design here that these products involve. So the first is a physical design. So there's the design for the case. The second is that there's an electronics design, so the design for the circuitry and so on. And then the third is that there's a computational design, so the design for the behavior of the object. So there are really three different sources of information and three different kind of sets of source code, if you will, that go into creating consumer electronic devices. So let me show you a couple of examples of other people's riffs on Dave's designs. So here's a set of speakers in the shape of an owl. Here's another, it's one of my favorites. Dave has done a whole series of artifacts. So the speakers was one. This is a radio. And then here are some people's riffs on that radio. One thing I'd like to mention here is that very quickly evident is the people's kind of personalization and customization of the physical form. But what is a little harder to see, but also very interesting, is people's customization of the electronics and also of the programming code. So there's one example here. You'll notice that most of the radios have two kind of potentiometers on the front. This one has one kind of knob switch, and then instead of having a knob here, it has this touch-sensitive switch. And so that's an example where someone hacked the electronics to put on this different kind of a switch. So we saw lots of interesting and different kinds of modification of these designs. Dave's most recent and most ambitious project is a cell phone. So this is Dave's DIY build-your-own cell phone. This has actually been his main phone for the past about 5 months now. So it works. He can get text messages and calls and send them and so on. And here are some shots of people chatting on their versions of Dave's phone at the conclusion of a build-your-own cell phone workshop. So if any of you are interested in building one of these devices, or a couple of others as well that I haven't shown, you should check out Dave's website, and you can download all of the information that you need to construct one of these things. So I encourage you to do that and then send us feedback about your experience and pictures. Okay, so consumer electronic devices is one area that we've been exploring. The next area that I wanted to talk about is paper sculpture, so interactive paper-based artworks. So let me tell you a little bit more about what I mean by showing you an example. I'm going to go ahead and stop that there, but yeah. So that beautiful piece was done by my student, Ji Chi, who's done just a whole range of gorgeous, gorgeous interactive paper works that I encourage you to check out and explore. But the other thing that she's been doing and that we've been doing together is helping people learn how to make things like that, and using those kinds of artifacts as a way to introduce people to electronics and programming. So I wanted to now share with you a few different techniques for working with paper and electronics in computation. So the first technique that I wanted to share is taping. So what I like about that example and what I wanted to say primarily about it is that this is so incredibly easy to do. So this was made just with paper and conductive tape and some really simple off-the-shelf electronic components and some Scotch tape. And using that super simple material palette, you can make a wide range of really cool stuff on paper. And I'll also mention that this was how that first piece that you saw the video of was made. So it was made entirely with copper tape and basic electronics. So it's actually not too far to go from here to that first piece that you saw. So we've been using these techniques and materials to introduce lots of people to electronics primarily. And so I wanted to show you some snapshots of that work and the stuff that other people have built with these tools. So here are a couple of kids actually playing with electronics, being introduced to electronics for the first time via these materials. These are images from a workshop that G taught just about a month ago. They're having fun. And then here's some snapshots of stuff that people made with these materials. Just simple electronics. This is another favorite. Okay, so that's one technique, taping. I wanted to now introduce another that's more about folding paper and making it fold itself. So what you see there is the use of a material called nitinol that has this wonderful property that when you heat it up, it changes shape. And one easy way to heat it up is to run electrical current through it. So we can combine those two things to make these shape changing structures. And because nitinol is very lightweight and delicate, it can be integrated into paper to make paper move in these really kind of wonderful and natural ways. So we've also been sharing these materials and techniques with people. This is a snapshot from a tutorial that you can find on our website about how to make that crane that flaps its wings. And then here's a snapshot from a workshop that we taught a couple of years ago where we had kids make their own cranes like this. Again, kind of their first introduction to electronics through these materials. I wanted to share one last technique for working with paper with you, and that's perhaps the most natural way of working with paper. That's drawing and sketching. So I'll just stop and say one thing about these examples. What I think is maybe most interesting to me, anyway, about these is the way that they let you approach electronics construction in a way that's visual and improvisational and very kind of fluid and natural. And that's just, those aren't qualities that we normally associate with electronics construction and building. So I wanted to share also a few of the things that other people have made using these materials and tools. And you start to see people make pretty interesting artifacts. I don't think I want to say too much about them. I'll kind of go on for too long, but I'll let you examine them themselves. I think this one is particularly interesting and speaks to the specific qualities of paint that make you think about doing things that you would never do with traditional electronics. In this case, kind of build circuit boards on three-dimensional objects like bowls. Here are snapshots from another workshop that was a little bit more recent. This is a project that was done by my student, Sam Jacoby. And what these are sketches that you actually then would clip a little circuit board to. And then each kind of separate line in the drawing becomes a point where you can record a voice or a sound that's associated with that part of the drawing. And then once it's recorded, you can touch that part of the drawing and play it back. And so this was this interactive storytelling workshop that he held where these young kids made these kind of comic book-like drawings and then animated them with their own voices, kind of telling their stories and associating them with the drawings. All right, so I wanted to share with you one other domain that we've been exploring. So I've talked about paper and I've talked about consumer electronic devices. I now wanted to talk about design and about digital fabrication. So many of you are probably aware that digital fabrication, so machines like laser cutters and 3D printers, are changing the way that we design things. And kind of one of the very interesting things from our perspective is that they're letting people design things that maybe they couldn't have designed or wouldn't have designed before. These are a couple of lovely examples. So these are both laser cut designs. So shown on the left is this lovely lampshade, laser cut out of paper made by Tord Bunche, and the laser cut evening gown, laser cut from leather, made by the designer Heider Ackerman. So there are these wonderful new tools that enable you to digitally design artifacts like this and then kind of very quickly produce them using tools like laser cutters. But by and large, these tools are only very accessible to kind of high-end designers, especially on the digital design side of things. So we're interested in making this kind of design cycle and practice accessible and engaging to novices. So we're interested in opening up this space. So my student, Jennifer Jacobs, is working on a new programming environment that's specifically designed to help people build their own digitally fabricated fashions. So this is what the environment looks like. So on the left, you have a layout that shows the garment that you're designing. And on the right, you have the programming code that generates that garment's design. So here you're looking at code that's specifying this lacy pattern for the center part of the garment. And these things are tightly coupled so that whenever you make an edit to your code here, your design kind of dynamically changes here. So you don't have to kind of go through a compilation process. There's really tight coupling between the code and the visual design that you see. Once you've coded the design that you like, once you've written the program that generates the most beautiful gown, say, you then export that, and it's digitally fabricated. So in this case, this design is sent to a laser cutter, which cuts out the pieces, and then you take those pieces and you sew them together to create a garment. So this is that garment that was designed in that sample program. And Jennifer just finished a workshop last weekend using this environment to teach kids to program. And I'll show you some of the results from that workshop as well as some earlier sessions. Let's see. So this previous weekend's workshop, the kids specifically designed and built these leather wristbands or bracelets. And so this is one kid's bracelet. Earlier this year, actually last summer, we had the chance to do a more extended workshop. This was over the course of several weeks. We worked with a group of high school and middle school students, and they had that time to design actually an entire garment as well as several accessories, and I'll show you some work that they did. So this was an activity where students wrote programs to generate these scarf patterns. The computer scientists in the room will recognize the Voronoi diagrams there. And then this was a final project that two girls worked on. So this is a program that they wrote to generate the pattern for this dress, which they then assembled. And then a wonderful kind of corollary to this experience for us was that the kids had the opportunity to showcase these designs at Boston Fashion Week. So the kids got to see their designs kind of modeled on the runway by these professional models. So that was a thrill for them and a lot of fun. Okay, so I've showed you a bunch of different projects that we've been working on. I now wanted to step back and just for a moment talk to you a little bit about why I think this work is interesting and why I'm excited about it and why I think it's worthwhile. So why should we be integrating art and craft and technology? I'm going to give you a few different reasons. So the first one is that I think this approach is actually a really great way to design new technology. So when you work with new and unexpected materials and tools, they naturally suggest new and unexpected contexts for technology. And so the wallpaper, to me, is one example of a potentially compelling technology that came about because of the materials and techniques that we were exploring. So we wouldn't have invented this technology had we not been using paint and had we not been thinking about these traditional craft practices surrounding arts and crafts era wallpaper. So this is a good and viable and compelling way to design technology, and one that's, I think, mostly completely overlooked by technology designers. So I think there's just lots of opportunity in this space if what your focus is technology design. But I think more interestingly for me, and more important for society, frankly, are some of the intellectual and social implications of these approaches. So another important reason, I think, to integrate art and craft and technology is that this integration can provide really new ways of thinking. And to illustrate that, let me share a picture with you. So this is a very simple circuit. So it consists of an LED light and a battery and a switch. And you can see that I'm pressing the switch here and turning the light on. So it's a circuit. It's also a drawing of a circuit. So if you will, it's a visual representation of a circuit. And it's also a schematic diagram. So if you look at it, the schematic symbol for the LED is here, and there's an LED embedded in that symbol, and the schematic symbol for a resistor is over there. And it actually turns out that if you draw like that, you're creating a resistor. So it's also a symbolic representation of a circuit. So this simple circuit on paper unifies three very different ways of thinking, just in itself as an object. So I don't want to push this too far, but I think there's a lot to ponder here. And finally, and most importantly, I think, this approach of integrating art and craft and technology is a wonderful way to engage new and diverse communities of people in technology creation. So our lives are increasingly kind of mediated and controlled and to some extent determined by technological devices. And we think that it's really important that the people who are designing those technologies are representative of our society. And right now, they're really, really not. So technology-related fields are some of the least diverse in modern society. And we believe that that's not because of any lack of aptitude on the part of the underrepresented people, but rather there's some interesting cultural thing going on that we can actually remedy. So a traditional way of approaching those challenges is to say, we need to unlock the clubhouse. This is a wonderful, wonderful phrase coined by Jane Margolis, who's a fantastic researcher in this area. So that approach says we need to make kind of technology communities more accessible and open to people. And I think that's absolutely important. But what I also think is we need to augment that approach with a very different one, which I call building new clubhouses. And what I mean by that is we need a thriving set of technology subcultures. So a thriving kind of set of really different spaces where people can explore and experiment with and play with and create technology. So we need spaces where these people can feel comfortable and at home. So we need to create those spaces where different kinds of people can feel like they have agency and they can naturally kind of identify culturally with those settings. And I think until we do that, technology-related fields are going to remain very, very homogeneous. And that's all I have to share with you today. But thank you very much. Sure. Yeah.
If anybody has any questions, Leah would be happy to take them. Go ahead in the back row.
Hi, I was wondering, I'm really interested in that pen that you were using for that. Is it commercially available, or this is something you guys are using out there?
So that pen is not commercially available yet. The people are working on getting it there. There are very similar materials that you can use. And if you go to our website, there are tutorials that describe like where you can get conductive paint and conductive ink. So.
Okay, so it is a type of conductive ink. Also, that battery pack you were using for that, I presume that's not a regular one like you can buy at Spark Plug. That's now some kind of thing where it touches the conductive paint on the bottom. Is that?
No, that's a regular battery, and you could buy. I mean, you could use any battery that you'd like with. Yeah, it's a very standard battery holder. They're also, the best thing to do is to make your own battery holder out of paper, and there's some wonderful examples of that on our site. And also, if you go to the Bear Conductive website, which is a manufacturer of conductive paint, they have some wonderful examples. So there are lots of good options. Yeah, that's a really great question, and something that always comes up as a question. Different materials there are different levels of expense associated with different kinds of materials. Some of them are very reasonable. So basic electronic components like LEDs and batteries are 10 cents and 20 cents, kind of on that order. So things like the conductive tape examples are very affordable, relatively very affordable examples. For a class of, 30 students or something, you might spend about $10 to $20. Other stuff is more expensive. Issues of kind of equity and access are things that we really care about. Locally, we're able to fund some educational outreach with our research funding. Clearly, it's a major challenge. Like the larger challenge is something that we can't address in that way, but it's something that we are sensitive to, and where we can, we try to do things like design reusable components that don't necessarily have to, be repurchased with each new project and so on. But there's no great solution to that problem. But there are a range of kind of expenses that you can associate with different projects, and there are some options that are very, very affordable. Actually, a lot of those decisions are largely pragmatic. So in today's world, kind of not doing open source work, trying to protect your intellectual property, can be much more expensive than not worrying about protecting your intellectual property. So a lot of the choices we have made have been frankly pragmatic. It's like open sourcing our tools and technology is a great way to have people adopt them and kind of use them in this meta way, if you will. I don't necessarily think that open source is appropriate for all circumstances. I do think it's very appropriate for some circumstances. And so we do try to make thoughtful choices about where it seems like open sourcing something will be really a benefit to the communities we're interested in reaching. And where it's less of a benefit, it's less of a focus for us. But
for the RIPs or the iterations that you showed, are those ones that are produced like through the internet, like from your website, or are they produced like directly from workshops? And
yeah.
the reason I'm asking is like who's approaching this technology?
Right. Almost all of the examples that I showed in this slideshow are people we directly interacted with in workshops. We do have some other work where we have much more kind of documentation of what other people have done, but I didn't show much of that today. But yeah.
I was wondering if it's too soon to tell, or if you have much data on what kind of follow-up there's been from, say, middle school kids, and you're talking about, I think it mostly about girls and people of color and underrepresented communities, if that's encouraging them to get more into broader electronics or STEM subjects, or is it kind of a one-off cool workshop kind of stuff?
Right. We have a little bit of information about that, but nothing. Nothing incredibly knock your socks off conclusive. I would say two things. We have very clear data that shows that kind of participating in one of the activities that we designed kind of increases people's kind of comfort with technology and their sense that it's something that they can do and that they're interested in. So we can show really positive outcomes on that front. We also have some data that's more about the LilyPad Arduino, which isn't a project that I talked about here, but that documents that real world in the wild use has these striking patterns, namely that it engages this large percentage of women who simply aren't engaging in any other normal electronics or programming communities. So those are that's the most specific data that we have. We haven't just been in a position to do large-scale educational studies that over long periods of time. It's something I'm very interested in. I'm not sure that we'll ever be the people to do that kind of work, since our focus is much more on the design and engineering side than it is on the educational research side. I don't know, if we get frustrated enough where we feel like we need to take on that role, maybe we would, but at this point, it hasn't been our focus. Mm-hmm.
We have a group called Co-Girl Science and Art Club for elementary school students. And on the app, we have a number of programs such as computer game design.
Mm-hmm.
Teach that was designed for older kids that we taught to their fifth graders, for example. So could you talk a little bit more about why you don't go to the elementary age? Because a lot of the literature and education now says get them as young as you can. So we're always looking for more volunteers who have the interest and the passion to work with them. We have an art tech lab on Saturdays for low-income housing development.
Right. Yeah, that sounds wonderful. We do work with younger students, and we certainly think it's incredibly important to support kids as young as possible, as you say. It's been, I think, a natural outcome of, I think, the projects, for whatever reason, that within our group that have been most exciting to us have naturally lended themselves to people of kind of middle school age and above. I think that might change at some point, and we might become really excited about a project that seemed especially appropriate for much younger kids. So it's not that we think that work isn't important to be doing, and it might be something that we focus on at some point. It just hasn't been a primary focus so far. But I think many of I think many of the activities that we've worked on are very appropriate for younger kids. So the taping circuits and the drawing circuits are both activities that we've done with very young audiences, and I think those are very appropriate. Some of the work that requires just longer in periods of time for investment or really high levels of kind of manual dexterity, we found that they were challenging to introduce to young people as groups. We found that some young people can excel at those things, but by and large, it's much harder to get a group of, say, 8-year-olds to do something that requires intense concentration and manual dexterity than it is to get them to do an activity that's not so challenging along those dimensions. So some are appropriate, and some, I think, are just appropriate for some younger students, but more challenging to introduce to kind of all younger students. Thank you.